And I'll hand over to you.
Yeah, it's great to be here. I will share my screen. Hopefully everyone can see that. I'll put it in presenter view. Perfect. Yes.
Yep, that's great.
Perfect. Thank you very much. So yeah, thank you for the organisers for allowing me to speak today. Yeah, I'm going to be talking about reconstructing Paleogene Atlantic Ocean circulation. I just want to say thank you to my collaborators. There are many, including all of the amazing scientists, crew and technicians on board that were on board during the South Atlantic Transect expeditions 390 and 393. So let's jump in. So why the Paleogene? So it's a particularly interesting interval, but for this audience, I don't really need to go into why paleoclimate studies are important, but they do really inform our potential future climate change that we're likely to see going on to 2100. So the Paleogene itself is a super warm interval of geological time. It's not going to be a perfect analog for future climate change, but it will be really important to understand these intervals of time, to understand possible processes and phenomenon, whether that's climate processes or the oceanographic processes that occurred during these warm climate states that potentially would be a high emission future for this planet. So the Paleogene itself composes the Paleocene, the Eocene, and the Oligocene. And during the early Eocene, we have this greenhouse warmth or this hothouse world where the planet Earth was very much warmer than it is today, around 12 to 14 degrees, depending on your proxy of choice, warmer than in the modern. And then the most striking feature that we have across the Paleogene is this gradual cooling trend that we see in this benthic delta 18O. Look, a laser pointer on so I can point. This benthic delta 18O, which we can consider a record of temperature through time. We see this gradual cooling trend leading into the Oligocene, where we have the large-scale glaciation of Antarctica for the first time. But so we've got this good understanding of temperature, whether that's deep temperature or surface temperature of the oceans. We have some understanding of the sea level during this time. And also we have a good understanding now through some recent work looking at the atmospheric CO2 concentration during this time. And around this early Eocene interval of times, around 50 million years ago, CO2 was a lot higher than it is today, around 1500 ppm, slowly decreasing as you go through the Cenozoic. But what we don't know too much about is the structure of the Atlantic Ocean circulation during particularly these warm intervals of time. And if we're heading towards a warm interval of Earth's future climate, then we need to understand these warm intervals of time really, really well. So I'm going to show this video. Hopefully it works for everyone. Hopefully it works. It did work in the practice. So this shows, this video shows the Atlantic meridional overturning circulation. So we see here warm waters moving up through the North Atlantic, cooling. And as they cool, they become more dense. And as they become more dense, they start to sink in a process called deep water formation. So these waters sink and flow at depth back into the North Atlantic, and they flow at depth away from the atmosphere and the surface oceans. And as it moves slowly southwards, it reaches into the low latitudes and the South Atlantic, where it mixes with deep waters forming from around the Southern Ocean, where some of this water gets upwelled into the upper oceans, but most travels on through the Southern Ocean into the Indian Oceans and Pacific Oceans, where eventually these waters travel to the low latitudes in these basins and upwell, completing this conveyor, this circulation system that we have today. Now, I want to go back to the start of this video because there's recent evidence that this northern surface waters is starting to weaken during the last sort of few hundreds of years. And this is linked potentially to our future climate change. So we need to understand this system really well in the warmer climates, because if this is starting to collapse now, what is the future going to be like? And our way of doing that is looking back at the geological record. So many studies have looked at ocean circulation across the last glacial maximum, or Termination 1. And although this is in a sort of the wrong thermodynamic direction, it is important to note that during this sort of last 20,000 years, studies have shown that AMOC has had various different modes. So, for example, during the Holocene and the Bolling-Alrod interval, where the climate was relatively warm, we had this modern-like AMOC structure. Whereas during intervals such as the Younger Dryas and the last glacial maximum itself, we had a slightly different colder mode of circulation system, where the northern source waters shoaled to more intermediate depths, whereas the Antarctic bottom waters dominated the abyss. And the main thing I want to take away from this is this shows the AMOC is a dynamic feature, and it is very sensitive to the background climate. So I just showed you that the AMOC is dynamic, but how do we actually go about reconstructing this in the geological record? So the most traditional methods use carbon and oxygen isotope systems, and they reproduce different components of the ocean system. So carbon isotopes can tell us information about the nutrient status of the water and the ventilation state. So this figure on the right here shows the modern carbon isotope sort of transect through the oceans today. And we see that the waters that form in the North Atlantic and flow down to depth, these tend to have really high values in delta 13C, because life in the upper oceans preferentially use up the lighter isotope, enriching or increasing the delta 13C of the water, and as it overturns and descends into depths, it takes that signal with it. Whereas in the Southern Ocean today, we have incomplete nutrient utilization. So therefore, the surface waters tend to have much lower delta 13C values. And so when they descend into the deep ocean, they impart that signal. So we can use delta 13C as a fingerprint for ocean pathways. Oxygen isotopes can give us information about temperature, salinity, ice volume, and these are really useful. So for the early Paleogene, when you have very little ice volume on the planet, on the continents, we can actually use the delta 18O as effectively a density proxy for your water mass, because the two factors controlling the delta 18O are the temperature and salinity. So we see here, this is just another sort of example of using stable isotopes as a way of reconstructing CO2. So this study looked over the Pleistocene, used carbon and oxygen isotopes to highlight that during this interval, just before the mid-Pleistocene transition, we had a very strong AMOC-like structure. So it's just a little case study there to show how we can start to reconstruct AMOC. Two other sort of proxies that we use typically are the radiocarbon cap delta 14C. This gives us an indication of the age, or the ventilation age, of a water mass since it was at surface exposed to the atmosphere. And we can use protactinium and thorium ratios again as a sort of a tracer for AMOC, the tracer for the strength of the AMOC. But the limitations of these two proxies is that they rely on very short half-lives. So we can't really use these far back in geological time. But again, another sort of quick case study here from Roberts et al. 2010, and they used all the proxies, or the different methods that I've talked about so far across the sort of LGMs the last 20,000 years. And what we see in this data set is that they all show very similar patterns. So we're very confident in all these different isotope systems are recording potentially ocean circulation signals. And the last one here at the bottom is neodymium isotopes, which is one of my favorite systems, which we use in the Paleogene. And I'm going to give a little brief introduction to the neodymium isotope system and how we use that in geological past. So neodymium isotopic compositions, they vary in space and time because of the radioactive decay of 147 samarium to 143 neodymium. So if you look in this figure on the top here, very old cratonic rocks from the Canadian Shield have a very different isotopic signature to, say, younger volcanic rocks that sort of boundary the Pacific Ocean. And that has an influence on the neodymium signature of these ocean basins, because when you weather that continent, when you weather the continent into the ocean, it will impart a very distinctive composition to the surface ocean. And then when in those regions of deep water formation, we can get that overturning, providing that signal into the deep ocean. And this works really nicely because the short residence time of neodymium in the oceans, compared to the mean mixing rate of the oceans, allows interbasin differences in neodymium. So effectively, neodymium can act as a provenance tracer for the deep water masses. Move on. Stop moving on. Okay. So some good ideas on some end member numbers to just keep in mind. So the Pacific, the modern day Pacific has a values of greater than -4 typically. The North Atlantic is very low, so -10s down to around -13.5. And the Southern Ocean is sort of in between an intermediate sort of value, reflecting the mixing of North Atlantic waters and Pacific waters around -7 to -9. And so what we can use is we can use various different substrates in the geological record to recover the neodymium isotopes. So we can use 4-arum coatings, we can use manganese iron crusts, fish teeth and debris, which is one of my favorites to use, and sediment leachates. We can use all these different substrates to get a time series record of ocean circulation in the past. And one of the strengths of the neodymium proxy is that, compared to others, is that it's not affected by biological fractionation process such as carbon and oxygen are. So it can act often very nicely coupled with the carbon isotopes and oxygen isotopes as an independent water mass proxy. So we see this in this study here from 2008, which shows neodymium and carbon isotopes across the last 100,000 years, and they have a really strong coupling, suggesting that both proxies are recording ocean circulation changes. So now I've gone through some of the background. We're going to now jump into the Paleogene ocean circulation and what we know so far. So across the Oligocene and Late Eocene interval of time, I'm just going to show a couple of case studies, some studies that with the very limited information that we have and what that might mean for this interval of time. So this first study looks at using neodymium isotopes from some Walvis Ridge sites. These is in the South Atlantic, and the 689 is in the Southern Ocean. And the main takeaway point from this study was that around 33 million years ago, so just after the Oligocene, the Eocene-Oligocene transition, we see this divergence in the neodymium isotope signal, with the South Atlantic sites deviating towards more negative values, suggesting a greater input of North Atlantic waters reaching the site, whereas the Southern Ocean site records very similar values, suggesting it's still being dominantly bathed by Southern Ocean waters. And then the second study looks at, and the main finding from this study was around this Oligocene, Eocene-Oligocene transition, EOT. We see the first evidence for the modern-like AMOT structure around just before this interval of time. So we're starting to see this northern source waters reach for the first time into the South Atlantic, bathing these Walvis Ridge sites that we know so well, and that there's this deeper cell from the Southern Ocean. But before the EO, or just before the EO, we're unsure whether this northern source waters really reached into the South Atlantic. So 2 more studies before we get on to some of my research is that, again, looking at this EO transition, isotopic evidence potentially suggests 1 to 2 million years before the EO transition, we start to see the northern source waters or northern component waters exported out of the North Atlantic for the first time, and potentially reaching the South Atlantic. And another study looked at some South Atlantic sites again, and some North Atlantic sites, and they used oxygen isotopes and what they did, they noticed a gradient between the North Atlantic and the South Atlantic, and they were suggesting that this is evidence potentially for different water masses bathing in the North Atlantic and the South Atlantic. So I've given you a little summary of the state of the art, but what do we know about the AMOC structure greater than 40 million years ago? And the quick answer is not very much, but I'm going to be showing the research that I'm contributing to this. So during my PhD, I focused in on the early Middle Eocene, so around 47 million years ago. So that's highlighted in this green box, and we've seen this figure already. This 47 million years ago, it's very proximal to this onset of this Cenozoic cooling trend, which is particularly interesting to see if what this ocean circulation is doing just after the start of this cooling trend. So around this time, there's two really interesting studies that have come out. One from Herbine et al. 2012, and they suggest around 49 million years ago, deep water formation was occurring within the Norwegian Greenland Sea region, and it flowed across the Greenland-Scotland Ridge into the North Atlantic for the first time. And this was really interesting finding from sedimentological evidence, and we look to provide some of the geochemical evidence to support this in a few slides' time. And then another study looked around the Eocene, the early Eocene, early Middle Eocene transition, at sites 1409, so the IDP sites 1409, we start to see this onset of this drift sedimentation. And this drift sedimentation data are chondrite deposits, and these chondrites, they are deposited from deep water masses. So these two studies suggest that around this time, so around the early Middle Eocene, we have deep waters forming in the North Atlantic, and they're bathing this region. So our approach in our study was to construct a meridional transit from the North Atlantic to the Southern Ocean, using multiple different sites, capturing the main different ocean basins. But what's really important when you want to reconstruct the AMOC over this large-scale feature like the AMOC is, you need to have some confidence that you're recovering and you're comparing the same stratigraphy at all your different sites. And the way we did that was to construct chemostratigraphic age models across all our sites. So I won't go into too much detail here, but these are our records using bulk carbon isotopes. And what we do is we use paleomagnetic datums and biostratigraphic datums to anchor ourselves in time. And then we complete intersite correlations to this site down here, so 1263, which is the Walvis Ridge site here, which has an astronomically tuned age model. So we can have good confidence that we're recovering the same stratigraphy at all our sites. And then with this framework, we can start to use our proxies to reconstruct the paleostratigraphy to answer the question, is there proxied evidence for an AMOC-like structure during this time? So here's some data from the PhD, and we thought the best approach would be to look at a mid part of a cycle. So this is an eccentricity solution. So this is effectively capturing the variability within the climate system. And we wanted to look over this mid part of the cycle because this would represent what we think is a mean climate state for the early Middle Eocene. And one key finding that we found is that we looked at the neodymium isotopes, this panel B here, and the purple record here is our North Atlantic data from site 1409, and it consistently records more non-radiogenic, so lower values than all our other Southern Hemisphere sites. And this is a really cool finding for two reasons, is that it gives us an indication that potentially the North Atlantic was bathed by a different water mass to the Southern Hemisphere, but also because the neodymium is recording really low values, we suggest that this water mass was formed in the North Atlantic or very proximal to the North Atlantic, which is a really interesting finding, which is supported by our two other studies I just talked about in the last few slides. And what I do then is also I couple this with carbon and oxygen isotope records. So we've got a coupled isotope approach. And what we see in these cross plots on the right is that we can identify and we can start to decipher the different water masses present. So what we suggest is that we have 3 different water masses present in the Atlantic. We have the northern source indicated heavily from the epsilon neodymium ratios at our sites. And then in the Southern Hemisphere, so in the South Atlantic and the Southern Ocean, we potentially have up to 2 different water masses. One sort of forms in the South Atlantic and base of South Atlantic, and one bays the intermediate Southern Ocean. And I'll show in a few slides' time a cross-section which will be able to see a bit more clearly what this means for the structure of the AMOC. But before we get there, I also want to touch on some work we did. We looked at the vertical carbon isotope gradients. So we compared our bulk isotope record with our benthic isotope records, and we basically produced a gradient. And what we noticed was that 2 of our sites had very low gradients. One was 700, which we suggest was a site of this deep water formation. Deep water formation, suggesting this vertical communication between the upper and lower as you convect waters. But also we noticed at 1258, this is a low latitude site in the Atlantic, has a really low gradient. And we suggest that to get this low gradient, you have to have a very well mixed ocean, and there has to be communication from the deep, from 3,000 meters water depth to the upper ocean. And the best way of our interpretation of that is that we have upwelling occurring at this site, which is really interesting. So the sort of findings from the last 2 slides are nicely sort of visually described in this cross-section you see here. So the Southern Ocean is on the left and the North Atlantic is on the right. And we see this 2-celled structure to the AMOC, where we have bipolar deep water formation, which occurs in the modern lake today, which is an interesting find that during the super warm world of the Eocene, we're still seeing bipolar deep water formation. And that these 2 water masses, they flow towards the low latitudes where we suggest upwelling takes place. We can see this in these figures on the right. This is the proxies and some transects through the ocean. We can see they show very nice trends towards the great water masses are flowing towards the low latitudes where we interpret them to upwell. So the next step was what I decided to do was to compare these proxies results with available modeling simulations. So I compared my proxy data to the DeepMIT models, which it's a project that looks into modeling the climate and the ocean circulation systems during the Paleogene. And what they ran a series of simulations. So we're looking focusing on the right-hand side. So this is 3 times in higher CO2, which reflects the Eocene sort of PCO2 values that we know of. And what we see is in the models, the most common feature in these models is that we have this Southern Ocean overturning. But what the models, only 2 of the models out of the series, were able to depict this North Atlantic overturning to approximately intermediate water depths. None of the models are able to fully reproduce what the proxies are suggesting, where we have this deep water formation occurring to depths of around 3,000 to 4,000 meters. So the next steps for this work is so the study that I looked at was a very short interval of time. So now we want to do is sort of broaden that to see whether this bipolar deep water formation that we found, was it a persistent feature across the early Middle Eocene, but also just more broadly across Paleogene? Or what we found is northern source waters, was it switching on and off? So did this deep water formation, was it permanent feature, or was it switching on and off? Because there's some really interesting studies that look at the boundary conditions, so the bathymetry and gateways in the North Atlantic. And these gateways and ridges are very sensitive. So potentially our future work may find that this northern source waters may switch on and off. And the other aspect of the study, which I'm working on currently, is does this AMOC-like structure that we found respond or show any sensitivity to orbital forcing? So is there variability in this AMOC-like structure? And if there is variability, what might be pacing that variability? So we're going to take a little pivot now to talking about the expedition that I was so lucky to go on last sort of springtime now. That was the South Atlantic Transect, expeditions 390 and 393. So I thought I'd give you a little brief sort of timeline of an IDP expedition, which I think is really important to understand how long these expeditions take to organize. So it started off in 2012 with a series of workshops, and eventually the outcome of these workshops led to a proposal being submitted and accepted. And then my involvement in the project came when I applied for a special call. So I applied for the special call, not thinking I would get on it as a second-year PhD student. But to my behold, I was very lucky and I was able to join. I was offered a space in the physical properties group. To be then, a few months later, COVID came along and unfortunately postponed these expeditions. So the science party could not go to sea. But what happened in the end was during the time slots for the expeditions, a skeleton crew of technicians and crew went out to our site and did a little bit of drilling and preparation engineering works to try and speed up. So when we did eventually go out there, we could crack on with the drilling and recovering our cores, and that would speed up potentially the research that we could get done. So we end up sailing 390 in April last year, April to June, and then 390 followed straight after from June to August. And this expedition was really, really interesting to be involved in because it was a multidisciplinary project. So it wasn't just a paleoceanographic cruise. There was multiple different objectives, which we'll talk briefly on in the next slide. But these sites that we were drilling are particularly interesting in that they went very close to DP, which is a predecessor of the IDP program, leg 3, which we see here, these sites here. And these sites provide some of the first evidence to really prove plate tectonics. So it was a really interesting place to potentially drill and see. So we were drilling into crust that ranged from 7 million years to 61 million years. So hopefully capturing all of the Paleogene for our research. So I touched on this a little bit. So the expedition objectives were multidisciplinary. So it encompassed all aspects of the Earth system, covering sort of the evolution of basalts and the timing and duration of mid-ocean ridge flank deposits, and how hydrothermal fluids travel through the basalt and how that might influence the biogeochemical cycling in the oceans. A second objective was the biosphere, so capturing and characterizing the communities of microbes within both the sediment and the basement, and particularly that interface between the sediment and basement. And then we had the sort of paleoclimate objectives, which I'll talk a little bit more about as this audience is more targeted towards that. And they were very nicely aligned to my personal research objectives. So the first objective that we had was to look and reconstruct the evolution of the deep water masses over the sort of 61 million year time interval, to answer questions such as, when did we first see the first evidence for northern source waters reach the South Atlantic? So we talked a little bit about that already in this talk. But there were other objectives, such as constraining the deep Western Atlantic carbonate compensation depth. So studies from previous expeditions across the mid-ocean Walvis Ridge suggests that the CCD was very dynamic through the Paleogene and potentially the Neogene as well. So we wanted to really provide some evidence to constrain this idea. And then the third objective was to look at the Cenozoic history of the sub-Atlantic gyre and how that may have developed through the Paleogene by monitoring proxies for productivity and looking at the nanoplankton or the planktic forams to get an idea of the paleobiogeography of the gyre itself. So what did we end up recovering? Well, we drilled 7 sites, and I will point you to the both 390 and 393 preliminary reports for all detailed information about what we recovered. So this is the 390 sites we drilled, and this is the 393 sites we drilled. And effectively, we almost completely recovered from 61 million years to modern. The only interval of time where we got maybe lack of or limited recovery was the Middle Eocene, which is a big shame for me because that's the interval that I'm particularly interested in. But we'll do our best with what we've got. I'll point out two really striking features that we found. So at the deeper sites of 1556 and 1557 here, in the sort of from the Oligocene to present, we saw these alternations between carbonates and clays. And this was quite a really interesting finding. And when we were drilling, it was quite bizarre is the wrong word, but like it was a striking feature, and it potentially suggests that CCD was very dynamic. It was shoaling, it was deepening over time. So there's people who are interested in CCD reconstructions are very happy with some of the records we recovered. And then people who interested in the early Paleogene stratigraphy, so at 1557, we recovered very expanded stratigraphy with sedimentation rates based on our age models of around 10 centimeters per kiloliter, which is really, really good for the deep site locations. And then one really cool find at 1557, we recovered the PTM, so the Paleocene-Eocene thermal maximum, this rapid warming event. We can see that here, this transition from carbonates to clays, suggesting maybe this carbonate dissolution associated with the PTM. So now this is the slide where I make everyone super jealous. So on an expedition, you've got 360-degree views of the ocean where you get the opportunity to see the sunset and sunrise with spectacular views. So I was sailed on the Joides Resolution. This is the first time I've been on the ship, and it was an amazing opportunity. Probably the best thing that I've done in my career to date. But on the ship, you need to remember this is a working lab. So I was in the physical properties group, and this shows one of the main track systems that we have to give that first characterization of the cores as they come up. So after curation of the cores, we were the first people to get hold of the cores and see what we'd recovered and start to analyze the cores. Next thing I want to highlight is the international aspect of the expedition. The crew, the technicians, the science party was truly international, and sharing those 2 months with those people was just amazing and a privilege to see people, see the scientists, the experts in their fields work in the various different aspects. So the multidisciplinary aspect, we learned so much about each other's disciplines during this time. It was a great experience. But again, you're on a ship for 2 months. Life continues. So you have to celebrate as you do with birthdays. So lots of birthdays on our expedition. So lots of cake and celebrating people's achievements as well. People were finishing their PhDs at the time or having successes with their publications. So it was a really nice atmosphere to be involved in. And also the expedition allows you to go to some amazing places around the world. So my expedition started in Cape Town. So I got to see lots of amazing wildlife, whales on the expedition, penguins went off after the expedition, and you get to see some spectacular places. So this is Cape Town looking down from Table Mountain. It's a real amazing place to go if you get the chance. So back to research before I get cut off by the organizers for making everyone super jealous. So what is the research I'm going to be involved in after the expedition is it sort of fits into these two nice broad categories. So looking at sort of rapid and major intervals of climate or oceanographic change. So I've touched on this already. So the Paleocene-Eocene thermal maximum, this rapid warming event. So it's very, very rapid, sort of 10,000 year onset. So it's the closest we can get in the geological to what is going on currently in terms of our rapid warming. Maybe there's some insights we can take from the PTM, but also looking at this transition, from this sort of really warm world of the Eocene into the Oligocene, this transition, seeing if there's any major ocean circulation changes occurring during this time interval. And then very importantly is this sort of, more importantly, I would argue, is actually looking at the background climate or oceanographic change, which really puts into context these rapid warming events, understanding what the structure of the ocean circulation was during this trend, this cooling trend. So I'm going to touch on some preliminary data that we've recovered. So I was very lucky to take some samples off the ship from 1556, and I've gone away and produced a neodymium record for this site. So this is what our sort of pilot, our preliminary data looks like so far. And there's some really striking features. And this is the major feature that we found, is this 2 to 2.5 epsilon unit increase in neodymium composition across this red clay layer unit. So this red clay unit, unfortunately, we don't have great age control over it because there's very low calcium carbonate to date with Biostrat. So the current age model we have is based on these, for this interval of time, is based on these two datums here. And currently we have to assume a linear sedimentation rate, and that's using that linear sedimentation rate, we can get an idea roughly of when we think this shift occurs. But there's a lot of, I will say there's a caveat with this, with the exact timing of this shift at the moment. Hopefully with some refined age model work, we can work out exactly when this shift occurs. But the shift exists. So I thought I would compare it to some existing data. So we saw this figure earlier on in the talk, and we see to the Walvis Ridge the darker black diamonds and triangles here, and we see some really interesting shifts at Walvis Ridge around this time as well. So when I plot that onto this graph on the left here, that's the data in green. So what we do see is there is this shift, but it's not as large as the shift that we see at our sites. And I also plot on this record is some data from 1090, which is the Agulhas Ridge, so South Atlantic, almost Southern Ocean signal. And what we see in this record is a very similar kind of trend, this increase in value, this increase in neodymium values to around -7, -6 composition. So maybe our shift is actually, maybe there's a small hiatus here, and maybe we're seeing the same event at 1556 as we're seeing at 1090. But what does this shift actually mean? Well, it could mean two different things. It could be a weathering, it could be a change, a big scale change in weathering that changes the inputs, maybe from Antarctica. Maybe we see a pulse of weathering of a source, a continent that has very high neodymium values, relatively speaking, and that might impart this basin-wide signal. Or could it be an oceanographic signal? Could it be a new water mass reaching this region? So here's my preliminary interpretations that if it is an ocean circulation signal, this increase in neodymium values potentially could provide us with some evidence that we may be starting to see a Pacific input to our sites. So this builds on the hypothesis of Scher and Martin in 2006 that suggests that the record at 1090, what we're seeing is this input from an opening Drake Passage of some Pacific waters flowing in across the Southern Ocean, bathing this region. But also our data then suggests maybe we're starting to see that water mass flowing and mixing and bathing the South Atlantic sites. But maybe the subdued signal that we're seeing at Walvis Ridge could be a function of it's a little bit further across the basin, or maybe some bathymetry or ridges play a part in reducing this export of the specific waters to Walvis Ridge. And that's what we might be seeing in our neodymium results. So what are our next steps? So our next steps are to finish off some work, the neodymium work at 1556, but then also produce some data from our sister sites, so 57 and 58, to start to get an understanding of the transect across the South Atlantic transect, to see whether we have any vertical water mass structure around this time. And again, it will be to start working on the rapid major climate intervals that I'll be working on as well. But before I end, I thought I'd just touch on my current position. So my new position at the University of Leicester, And here's sort of an organization tree of where University of Leicester fits in with in IDP and within ECORD itself. So University of Leicester works with Montpellier within the European Petrophysics Consortium, and we sit in ESO, which is the ECORD science operator. So ECORD, in the next slide, I'll talk about missions to platforms, which is what ECO operates on behalf of IADP. So, and what we specialize in is providing assistance in the downhole logging and the core physical properties work throughout a whole expedition timeline. So from proposal, going to meetings, going to planning those planning meetings that set up these expeditions, all the way through the offshore phase of the expedition and the onshore phase, because on MSPs there's an onshore science phase as well as offshore, and then continuing on with research afterwards. So mission-specific platforms are the ECORD's platform that they contribute toward in IDP. And we've run various different platforms throughout the last sort of 20 years now. And you can see some here, various different objectives, lots of paleo objectives, from looking at sea level change at Tahiti and the Great Barrier Reef, looking at drilling into the Chicxulub mass impact crater to understand the climate during that time, during that event. And what we do is on these mission-specific platforms, we contract out a ship specialized for the expedition. So we can drill in locations which the other big ships in the IDP program can't get to. So such as the Arctic here, we have icebreaker ships that help us stay in position. And then we can also drill in very shallow waters, such as the Chicxulub crater. So I wanted to highlight that just because the current IDP program is finishing and the JR is retiring, there is still opportunities to be involved in scientific ocean drilling, and ECORD and the mission-specific platforms is a great opportunity to be involved. So here is a summary of my talk. So what we found during some of our research is that we have bipolar deep water formation in the early Middle Eocene during this super warm world. It reached potentially the low latitudes. It may not have reached the South Atlantic during this time, but what we need to do now is look if this is a persistent feature. And then we're starting to work on the South Atlantic transect samples. We're starting to find maybe some evidence of a early sort of middle to late Eocene opening of Drake Passage, similar to other hypotheses today. So I will finish there, and I'm happy to take any questions. Thanks, everyone.